Okay, so next let's look at inductor. So inductor is considered as a dual of a capacitor. So instead of storing energy in electric field, inductor stores energy in magnetic field. And the symbol of the inductor looks very much like a resistor, but not quite. Okay, but as you will see, it sort of behaves like a resistor, but there is a subtle there's some difference um, between the two, as I will discuss shortly. So an inductor has a unit of Henry, denoted by H. Okay, and a typical range of value goes from 1 nanohenry to 10 Henry. So again, larger the value, meaning larger the footprint of your, or the physical dimension, physical size of your inductor. And inductance is a measure of device to store energy in the form of magnetic field, as we discussed. So we look at the voltage across an inductor, okay, and also the current through an inductor. What we see here is that we can use this equation V of t, okay, which is equal to L times DIL, okay, over dt. Okay, so IL is the current passing through this inductor, and VL is the voltage drop across this inductor. And the reason that I say this inductor uh, behaves similar to a resistor is that if you look at a resistor, right? So by using Ohm's law, okay? So we know that V is equal to I times R, or I can say R times I. Okay. And if you compare this equation to this on the left, okay, so V is equal to L, okay, so the inductance times not the current, but the change in the current with respect to time. Okay. So in other words, if a resistor, okay, is opposing the current passing through this resistor itself, okay, an inductor is opposing not the current, okay, but is opposing the changes in the current passing through it, okay, because we see that this is DIL over dt, okay, it's opposing the changes in the current with respect to time, not the absolute current itself, but the changes in the current, okay, passing through this inductor. Okay, so if I want to rewrite this inductance L, right? So I can say L is equal to V over not the current I, but the changes in the current with respect to time. Okay, DIL over dt, right? So that's how one way you can understand the similarity between this inductor and the resistor. Okay, and with that, you can also see that the way this inductor is drawn, right, looks sort of similar to um, to a resistor, right? So an inductor, okay, consists of some coils, okay, and which looks sort of similar to this symbol that we are all familiar with for a resistor. Okay, so to express the current passing through this inductor, what we can do, just like before, we can just take integral on both sides, right? So the integral will get rid of the derivative. So we take the integral on both sides, move things around. So you're going to see that IL is equal to integral of VL t from t0 to t plus IL of t. Okay, and notice that I need to add 1 over L over here to complete the equation. Okay, so this is 1 over L times the integral of this something, okay, including the initial condition. All right, so let's look at some more properties. Okay, so by duality, in the capacitor, discussion, we learned that a capacitor can block DC. Okay, it blocks DC, it blocks constant current. In the context of an inductor, the duality applies, right? It's sort of opposite. Okay, so for an inductor, it actually passes DC. It does not block DC, but it passes DC. Okay, it passes DC. Okay, and I'm going to show you why that is the case. And it can also potentially block, okay, high frequency signal. Okay, and this is something that we will also discuss a little bit more extensively when we look at the frequency domain analysis. Okay, so let's for now focus on the time domain representation. So, for example, if so this is versus time. So if the inductor current, okay, inductor current is a constant. Okay, so let's say phi m. Right, phi m here. So this is my IDC phi m. Okay. So to calculate the voltage drop across this inductor, okay, all I have to do is I take the L times DIL over dt. Okay, whatever that inductor is or the inductance is, and I take that multiplied by the change in the current with respect to time, DIL over dt. Okay, so when I take the derivative of this IL of t, and I'm basically getting a zero, right? Because derivative of a constant again will give us zero. Okay, so this term here is going to give us zero, right? It's derivative of constant. Okay, so 0 times L again is equal to 0. Okay, so what does that tell you? Well, so if I voltage, okay, the voltage drop, well, this is the context here. So this is VL and this is L. Okay, so if VL is equal to 0, right? So that means the voltage drop between this point and this point, right? If you take the difference, it will give you 0. There's no voltage drop. So that means this voltage and this voltage are same. And this basically tells you that your inductor looks like a short at DC, right? At DC meaning 0 hertz, no, 0 hertz. Direct current is constant. Okay, so at DC, inductor behaves just like a short because VL is equal to 0. Okay, so these 2 points are sort of shorted out or they are tied together. Okay, as if this inductor is not there, but it's replaced now by a piece of wire. That's all. Okay, so this is sort of presenting an opposite behavior of a capacitor at DC. Okay, at DC, the capacitor behaves like an open, while inductor behaves like a short. Okay, duality. Okay, duality. Okay, so however, at high frequency, as frequency goes up, okay, the rate of change in the current also goes up, right? So this frequency, when F goes up, right, which I can sort of see by looking at the rate of change, d over dt, okay, di over dt, right? Because I is sort of the subject here, right? So I wanted to look at how fast this current is changing with respect to time. The faster it's going up and down, right? Then the higher the frequency, right? This is again versus time. So the higher this is going up and down, right? So the higher frequency, so therefore higher the rate of change, therefore F goes up, right? So when this d IL over dt, okay, goes up, okay, which tells you that it's no longer equal to 0. So that means VL has to be equal to something, right, other than 0. Okay. So that is the reason why if you look at this equation here, it's only when the inductor is used at DC, then can it behave exactly like a short, okay? Anything other than a DC, right, it's going to look like it's not going to give you a short, basically, right? It no longer behaves like a short just because VL in that case is not equal to 0. So if VL is not equal to 0, then you can no longer say you have a short. Okay. And that's just because dIL over dt is no longer equal to 0. So VL is equal to something now, which is not equal to 0. Okay, so we'll come back to revisit this when we talk about the frequency domain analysis again, right? But we'll sort of compare the time and the frequency um, domain analysis in this context. Okay, so let's look at how can we calculate the inductance of simple solenoid. So you may have seen something like this in your physics class. So I have a solenoid here. This is like your magnetic core, and I can use some wire coil to coil around certain length for the winding. And then I also have some area corresponding to this magnetic core, and I inject the current passing through this wire, and I can determine to first order how much my inductance is. So this L depends on mu, which is your permeability. Okay, so mu naught mu r, right? So mu r is relative permeability depending on the material that we have. So we have magnetic core here, magnetic material. So mu r is going to be greater than 1 in this case. And times n squared, where n is the number of turns shown over here, and the A, right, is the cross-section area of the core itself. And length is the L is the length of the winding. So from here, you can see that L can be increased by decreasing the length of the winding, right? By packing these coils, okay, between each other closer, okay? And you can increase the inductance, or you can increase the area of the core, okay? Or the number of turns, right? And in fact, when you increase the number of turns, right, you actually get a quadratic improvement in the in your inductance. Correct. It is n squared, right? Quadratic increase. Okay. Okay, so similarly for energy stored in an inductor, right? So we're going to use this same approach here, work done, right? W is equal to integral of power with respect to time. And power, as we know, is V times I. And this V can be expressed by L dIL over dt, right? So VL is equal to L dIL over dt, right? So this is to compare with IC is equal to C dVC over dt, right? So one is for capacitor and the other one is for inductor, okay? So in this case, we replace the VL by L dIL over dt over here. And just like before, d tau and d tau cancel. And we can take the L out, right? This is just a constant. And we do the integral of IL with respect to DIL. And again, we have the IL at T0 and IL at T. IL at T0 denotes your initial condition, right? Just like before, like your capacitor. If there's some initial voltage sitting in your capacitor, then you have to account for that. Similarly, in this context, if you have some initial current passing through this inductor, then you have to account for this IL at T0 as well, okay? So then once you work out the mass, and then you will see that it's following pretty much the same form as what we saw for the capacitor earlier. So for capacitor, we have half CV squared, okay? And for inductor, we have half Li squared, okay? So, okay. Right. So by the same token, instead of saying charging and discharging the capacitor, in the context of inductor, we will use energizing and de-energizing an inductor. So if V, L, and IL are larger than 0, okay, or they're positive, then we say that the inductor is being energized. Okay? And the opposite is true if VL and IL are negative or less than 0, then we say that the inductor is being de-energized. Okay? De-energized. Okay, so the last topic here. So going back to the continuity property of a capacitor, right? So earlier we talked about the voltage drop across a capacitor cannot change instantaneously. Okay, so in the context of inductor, the duality again applies, right? So instead of saying voltage drop across a capacitor, right? So we will say the current passing through an inductor, right? So instead of using VC, we will use IL. Okay, so IL at 0 plus is equal to IL at 0 minus. Okay, so the current passing through an inductor cannot change instantaneously. Okay, it can change gradually, but it cannot change instantaneously. Okay, so again, it's the same example, same rationale here. So if I'm trying to energize an inductor by looking at the current passing through it. So let's say if I want to go from 0 amp to 5 amp, right? And this is again T1, this is T2. So delta T is equal to T2 minus T1. Okay. So if I want this to happen gradually, okay, so that's completely fine, right? So it's going to take some time for this inductor to be energized, right? For the current to ramp up from, let's say, 0 to 5 amp. Okay? And this is the amount of voltage that you will need, right? Because we know VL is equal to DIL over DT times L over here. Okay, so I divided by L again down here so that I can normalize the L out, and I can just look at the simple derivative of this ramp. Okay, so this is the amount of voltage that I need in order to energize this inductor going from 0 to 5 amp within, let's say, a period of 2 hours, a duration of 2 hours. Okay, so this is completely okay. Now, of course, the scenario is slightly different if we say, okay, well, I wanted to go from 0 to 5 amp in no time, where right now this delta T is equal to 0. Say, okay, I can't really wait for this inductor to be energized. I want this to happen suddenly or instantaneously, going from 0 to 5. Then unfortunately, this is not possible because unless you have an infinite amount of infinitely large voltage, okay, you need to impose an infinitely large voltage so that you can make this happen. But we know this is not practical. Okay, so there's a note here. Again, the current passing through an inductor cannot change instantaneously. It cannot change suddenly. However, it can change gradually. It can change slowly. Okay, and this is again sort of summarized by this property of continuity equation. Okay, so instead of using Vc at t0 plus and is equal to Vc at t0 minus. So we'll use the IL. Okay, so IL at T0 plus is equal to IL at T0 minus. Okay, following exactly the same rationale as we discussed for the capacitor case. Okay, so no sudden change is allowed. Okay, gradual change is fine. Okay, and following the property of continuity or continuity property. Okay, so just like a capacitor, right? So in duality of a capacitor, instead of having this um, inductor behave like a voltage source or like a battery, right? So momentarily, this inductor is going to actually behave like a current source. Okay, it's actually like a current source, not a voltage source. Okay, so and that kind of makes sense because now we are really looking at the IL, right? Inductor current. So the inductor current, okay, right at this moment, and has to be equal to the inductor current at this moment. Okay, so at that very instant of time, right, momentarily, it actually behaves just like a current source, right, following this continuum, right, or continuity. Okay. Um, okay.